Right. Today we're going to talk about hypothesis testing on a population mean. And before I get started, I'm going to just back up for a minute and talk about what is hypothesis testing. So, hypothesis testing has a statement about the population value. And in this case, that's the mean. Okay. And one thing that's very important to remember is that the null hypothesis, H0, is always a statement of equality. So the mean is equal to some value. The alternative, which is called HA here, okay, that is always a statement of inequality. So the mean is less than the hypothesized value in H0 or greater than or not equal to. And those are the three forms that we're going to deal with in this section. Now, the null hypothesis is generally what's believed to be true about the mean or the status quo, and the alternative hypothesis is what you want to prove about the mean. Okay, let me give you a quick example. Okay, so an economist believes that we have entered a recession and that the mean wage of adults aged 18 and older has decreased from $16.25 an hour. To test this hypothesis at the 5% significance level, a sample of 30 individuals is taken, and it's found that the sample average is 1490, with a sample standard deviation of 375. What should the economist conclude? Okay, so let's just write down the given information, because there's a lot of information that's given here. So first, let's just decide on the null and the alternative. The null hypothesis is what's currently true, and that is that the population mean wage is $16.25. Okay, that's the status quo. The alternative, what the economist wishes to establish, is that this wage has decreased. Okay, so the statement of the alternative is that the mean is less than. Okay. And when you perform a hypothesis test, you are more or less trying to decide for practical purposes between the null and the alternative. And you're going to make your decision based on data and the evidence provided, as well as the strength of the data. Is it conclusive? Is it suggestive? Do you not have enough data to make a conclusion against the null? So these are questions that we're going to have to answer. Now, let me just talk about the outcomes of the decision. Okay. So there's a decision that you have to make that's reflected in this first column. The terminology that we use as statisticians is not that we accept the null hypothesis. It doesn't mean that it's true. The terminology we use is that we fail to reject the null hypothesis. And for practical purposes, you might say that we accept the null, but as statisticians, it could be that there's just not enough evidence to reject the null hypothesis. That it suggests that the null hypothesis is false, but you don't have enough evidence, you don't have enough data to reject it. Okay. Then you could make a decision that you're going to reject the null hypothesis, and that doesn't mean that you believe the alternative hypothesis is true, ironically or not, but for practical purposes it does. Okay. What it means is that the evidence or the data does not support the null hypothesis. Okay, and therefore you're going to reject it. Okay. Now, there could be a reality to the situation. The reality could be that the null hypothesis is true. That's reflected here. Or the reality could be that the alternative hypothesis is true. Now let's look at your decision. If you fail to reject the null, that's this second row. And failing to reject the null means that you're going to, for practical purposes, conclude that the null hypothesis is true. And if the reality is the null hypothesis is true, that's a great thing. And so we got this smiley face. Now, you could fail to reject the null hypothesis. So that could be your decision. But the reality could be that the alternative is true. Okay. In that case, you've made an error, and that's called a type 2 error, is when you fail to reject H0 when the alternative is true. And we got a little sad face there. Now, in this last row, your decision is to reject the null hypothesis. For practical purposes, we'll say that you're accepting the alternative. Well, if in fact the reality is that the null is true and you reject it, well, you made a type 1 error, and that's a very sad thing. If you reject the null hypothesis and the alternative is true, well, that's a good thing. Because for practical purposes, that means that you're going to accept the alternative. Okay. Now, in this section, we're dealing exclusively with population means. And the thing that estimates the population mean is the sample average. So we're going to make our decisions based on the sample average and how much of an error we're willing to make. Okay. And by how much, I mean a probability. Okay. So in the example that we've talked about right here, if we observe a sample average, which is called X bar, that is small, that's evidence in favor of the alternative, H sub A. And so we're going to reject the null hypothesis in favor of the alternative if the sample average is small. And how small we have to determine. We have to use the given information to say how much of a deviation from 1625 could be seen in a sample average, and how much of that would we say is due to random chance versus how much of it is due to the fact that the mean is actually decreased and is less than 1625. Okay. Well, we have the sampling distribution, or the central limit theorem, that tells us exactly that. It tells us if the mean is some specific number, what's the probability of observing a sample average? Okay. Okay. So the key point here is that a small value of the sample average is going to be evidence in favor of the alternative. Okay. Now we're going to make our decisions based on what's called a significance level alpha, and that is the type 1 error. So alpha is the risk of making a type 1 error, and we're going to specify it here. In this problem, alpha was 5%. That's the significance level. Okay. So here we're going to make our decision, and we have a very fortunate statistic that involves our sample average X bar, our hypothesized mean mu, our sample standard deviation S from our data divided by the square root of n. So using this statistic, we're going to calculate the type 1 errors and evaluate between the null and the alternative to test hypothesis. Okay. Now a key fact here is that we're using the sample standard deviation S, and we're going to assume some things if we're going to use this formula. Our assumption is that data is independent, or we have a random sample. The data is normally distributed, or we have a large enough sample size, n is at least 30, and the data is identically distributed. Now the data is identically distributed is just saying that you're sampling all of your observations from the same population, or that they're undergoing the same fundamental experiment. Okay? Now, I had alluded to different forms of the alternative, and there are 3 different forms, and let's have a look at them. Okay? So the situation that we're dealing with is that the alternative is less than some value. The some value is mu naught. So we're testing the hypothesis that the mean has decreased. That is the scenario that we are in right here. And here there's a rejection region and there's a level of alpha right here. Okay, so we're specifying alpha as 5% and there corresponds a rejection region. Okay, that is a region for which if x bar is less than that value, i.e. small enough, we reject the null hypothesis in favor of the alternative and conclude that the wage has decreased. Here's an alternate form, which is instead of the mean decreasing, the mean increases. And the rejection region is to the right. Now, for us, we're going to use x bar. And the question is, has x bar evidence in favor of the alternative would be if x bar is large, if it's increased. And we have to determine how large. And based on this level of alpha in the given data, we're going to calculate what this rejection region is and say if it's large enough. Okay. Now, a third form of the alternative is just that the mean has changed. You don't know if it's increased, you don't know if it's decreased, you just believe it's not true. And there are two forms in which the mean cannot be equal to some number. It could have decreased or it could have increased. So there's two rejection regions. You're going to reject it if the mean is bigger than h0 in this rejection in the right tail or less than this value. Now, another way to test this, and this is only for this alternative, the mean not being equal, is to construct a confidence interval with a 1 minus alpha % confidence interval. If 0 is contained in the interval, you will fail to reject the null hypothesis. If 0 is not in this interval, if the mean mu naught is not in the interval, you will reject it. And if it is in the interval, you'll fail to reject it. Okay. Now, another way of testing these hypotheses is with what's called a p-value, and if the p-value is less than alpha, you reject your null hypothesis. Okay, so let's finish off this problem. So this was our original problem. And here's the given information. So the first thing that you should do is you should write down your null and your alternative. Okay. We have a sample size of 30. And we have degrees of freedom that is n-1, so 29. And we have a sample standard deviation. Now, something that's very important is x bar. And x bar is 14.90. And that points in the direction of the alternative. But the question is that due to random sampling that the sample mean is less than the population mean? Or does this indicate that the population mean has actually decreased? Okay, so we're going to test this at the 5% level of significance. Okay, so we're going to use the critical value method. But another method you should be aware of is the p-value method. Okay, but let's proceed with the critical value method. We're going to reject the null hypothesis if the odds of observing the data under the null is less than the critical value of alpha. And the data we observed is going to be calculated by a sample average x bar. Okay, we're going to determine the rejection region, and the rejection region depends on the alternative HA. Okay, in this case, since our null hypothesis is less than, we reject if the sample average is less than the critical value. Okay, so our rejection region is determined by our alternative hypothesis. Here it will be less than the mean, here it will be greater than, so your alternative does play a role. Okay. So one thing that's very important is I'm going to calculate the probability that the sample average is in the rejection region. And I want 5% of that area to correspond to that, because that is the probability of a type 1 error. Okay. So x bar is in the rejection rejection region, I'm going to make a type 1 error. So remember, x bar minus the mean divided by s over root n. This gives me a t-distribution, so I get that over here. Now I'm going to do this to both sides. So that means the rejection region, and I'm making a type 1 error. So the true value of the mean is given by, the true value of the mean is given by this. I'm making a type 1 error, okay? So type 1 error means that I'm going to reject the null when the null is true. And the null being true means that the mean is 1625. Okay, so 1625, I subtract that. I have my sample standard deviation. I have root n, which is root of 30. And that gives me a t-distribution. Now, one thing to note is that if I want 5% of the area of a t-distribution to be less than 1.699, that is the value that corresponds to the 5th percentile. And I can determine the value of 1.699 using an online calculator. Okay. So I'm going to do the inverse t-distribution. And let's see. I have 29 degrees of freedom. Yep, 29 degrees of freedom. And the confidence level that you're going to choose is the one that is double. So instead, I want 5% in each tail, so that means 90% is in between. So when you're doing hypothesis tests that are one-sided, you have to double alpha. So alpha was 5%, and I do 100 minus 2 alpha gives me 90%, and that gives me 1.699. So that's how I determine that value. So that value is 1.699. And to determine the rejection region, I set this quantity equal to this quantity. After all, they're equal. So I have to do some algebra and just solve for these two values. So I get the rejection region is given by 16.25 minus 1.699 times 3.25 over root 30. So if the sample average is 15.2 or less, I'm going to reject the null hypothesis in favor of the alternative. Okay. Now, since our sample average is 14.9, and that's less than 15.2, it is in the rejection region, and we reject it at that level of significance. This significant level of significance will change the value for rejection. Okay. Okay, so I mentioned that there's another method, and this one's called the p-value. You can use whichever method you prefer, but in future sections, we're going to use the p-value a little bit more prominently. Okay, and the p-value method says, what is the probability of observing x bar being 14.9 or less? After all, 14.9 was the actual observed value, so what's the probability it's at most that value? Okay, and why is it less than here? Well, this less than comes from the alternative hypothesis. So HA is that the mean is less than 1625. Remember, our sample average is what indicates between the null hypothesis and the alternative hypothesis. So if the sample mean is less than, that's evidence in favor of the alternative. Okay, remember our form of our hypothesis testing. So the mean is less than. So that's why we have a less than. It comes from the alternative hypothesis. Okay. Okay. So I want to calculate this probability. What I'm going to do is I want this probability to be reflective of a type 1 error. So I'm going to, under the type 1 error, I'm going to assume that the mean here, which comes from the null hypothesis, is this 1625. So remember, our mean states that under the null, the mean is 1625. So we're going to assume that to be true. And so that's why we have 1625 here. I divide by the sample standard deviation over root 30. Wait, that gives me a t-distribution with 29 degrees of freedom. The number right here is minus 2.27. So I want to calculate this probability that the t-distribution is less than 2.27. Now, you can go ahead and use this online calculator, and here they list them all. I'm going to use just the normal t-distribution. So I'm going to go to this one. I have 29 degrees of freedom. Excuse me. 29 degrees of freedom goes there. And I have this t, so I need that t value. T value is minus 2.27. And now it tells me the p-value, but it's two-tailed, okay? So if I want to get the actual p-value, I'm not in the two-tailed scenario because my alternative hypothesis is just less than, okay? So one-tailed tests are the mean is less than or the mean is greater than. Two-tailed would be not equal to. So if I want to get my two-tailed, if I want a one-tailed test, I'm going to take this number, 3.08, okay, and I'm going to divide it by 2. So this number right here, this 0.015 is 0.0308 divided by 2, okay? So I take that 0.0308 and I divide it by 2 and I get 1.5%. Okay. Now, since the p-value is less than 1.5%, that's less than the cutoff value of 5%. So we'll reject the null hypothesis in favor of the alternative. Okay. So this p-value gives a little bit more accurate information. It tells us that it will be significant up to the 1.5% significance level, okay? So even at the 2% significance level, you'd reject this, okay? Okay, let's do another example. So here we have an exercise scientist, and this scientist believes that in recent time, the mean amount of time spent exercising has changed from 40 minutes a day. To test this claim, a sample of 49 individuals is taken, and a sample average of 45 minutes is calculated, with a sample standard deviation of 28 minutes. We're going to test this hypothesis at the 5% significance level. Okay, so the first thing that you need to do is just determine between the null and the alternative. So your null is a statement of equality. It believes that it's changed from 40 minutes. So your null is that the mean is equal to 40 minutes. Your alternative has to be a statement of inequality. The exercise scientists didn't say how they believe things have changed, so we're just going to put not equal. Okay. The sample size is 49. So we have 48 degrees of freedom. DF is 48. The sample standard deviation is 28 minutes. The significance level is 5%. The sample average is 45 minutes. And alpha over 2 is 2.5%. Okay. So let's go ahead with this hypothesis test. We've identified all the given information. First thing is just to write down your null and your alternative hypothesis, and then every piece of information that's given to you. Okay. So we're going to use the two-sided hypothesis, and there's a symmetric rejection region. Okay, and that's because we're in this scenario now. The alternative is that the mean is not equal to mu 0. Okay. Okay. So 5% needs to be equal to the probability x bar is less than the rejection region. It's in the negative portion, or that x bar is bigger than some critical value in the rejection region. Now, since we have symmetry, this says that twice the probability that x bar is bigger than r needs to be equal to 5%. So in other words, 2.5% is equal to this probability. The absolute value of X bar is bigger than the rejection region. Now, if I want to calculate probabilities with X bar, I'm just going to subtract the mean. And the mean under the null hypothesis is 40 minutes. Divide by the standard deviation, that's 28 minutes, and the sample size is 49. So I'm going to get the rejection region minus 40 over 28 divided by root 49. This gives me a t-distribution. Anytime I have X bar minus mean over S over root n, I get a t-distribution. And it's the probability the t-distribution is bigger than 2.01. Okay, so here I have a t-distribution, and I'm going to obtain 2.01. You might ask, how did I get 2.01? Okay, I'm going to show you. Okay. So here's our list of calculators. I have the inverse t-distribution. 95% confidence means that I have 2.5% of the area in each curve, which is exactly the scenario that I have. I have 48 degrees of freedom, and I'm just going to calculate that. That's 2.01. Okay, so that's how I obtain this number. You can also use your tables for all of these. You do not have to use the calculator that's online, but I think the calculator online is probably the most convenient. Okay. So I just set this quantity equal to this quantity. So I solve for this, and we solve for R. Okay. Now, when I solve for R, my apologies, there's a little bit of a typo. That should be 4t. This whole thing should be this. Okay. And because there's a plus or minus, because there's an absolute value, there's a plus or minus there. Okay. So I set this quantity equal to this quantity, which comes from here. Okay. Then I go ahead and solve for R, and it gives me this value. Okay, so I'm going to reject if X bar is too big, if it's 48.04 minutes or greater, or if it's less than 31.96 minutes. Okay, and notice this is equivalent to just constructing a 95% confidence interval for the mean. And if the sample average is in the confidence interval, we fail to reject it. Otherwise, we reject the null hypothesis. Now, because this X bar is 45, it's not in the rejection region for the greater. It's not greater than 48.04, and it's not less than 31.96. So we fail to reject the null hypothesis. Okay, even though the sample average is bigger than 40, it's not big enough. It could be due to random chance, or it could be due to the fact that the mean has increased. We just don't have enough evidence to conclude that the mean has increased. We need a larger sample size so that the data would be more clear. Okay. Now here's a case study, and this corresponds to both the material in this section and also what's called a match pair design for comparing two population means, in which the two data are correlated. But let's proceed with this case study. And the question is, are there any psychological indicators associated with schizophrenia? So in 1999, researchers reported the results of a study that controlled for genetic and socioeconomic differences by examining 15 pairs of monozygotic twins, where one of the twins was schizophrenic and the other was not. The researchers used MRI to measure the volumes of the brains of these twins. So in one twin there's an affected one, and in the other there's an unaffected. Or in one twin there's a schizophrenic, and in one there's a not. And the question is, are the brain sizes of these the two populations different. Okay? And your data looks like this. You have a non-schizophrenic twin, an unaffected, and you have an affected twin, a schizophrenic one. And here are the corresponding brain sizes for the unaffected versus affected. Now I have a matched pair data, meaning that someone perfectly matches up with the other individual, and that's the twin. And we love this kind of data. It's one of the most powerful and important kind of data that allows for comparisons, because in the affected versus unaffected, if we've controlled for income within the parents, potential schooling differences, potentially geographic location, because they're going to be raised by the same family typically. And so we've controlled for many, many confounding factors. Okay? And so we just take the difference between the data of the twin. Now, if we didn't take the difference, we might not have all the assumptions satisfied. I'll circle back and talk about that later. But this difference boils down to a test of hypothesis, and we're just going to look at this difference. Okay. So why take the difference? I've talked about the fact that they're perfectly matched up as a natural comparison for one versus the other, and that allows us to look to account for different confounding factors. Okay, we're going to test if we believe that there is. If we're going to test the hypothesis that the mean difference is 0 versus the mean difference is not 0, that's equivalent to testing the hypothesis that the mean of the affected, the schizophrenic, is equal to the mean of the unaffected. Because if they're equal, then the average difference should be 0. Versus the hypothesis that the unaffected is not equal to the affected. Okay, so if this is true, then the mean difference should not be 0. So this allows us to test two populations, and the two population test would be here. These two forms are equivalent. I haven't talked about this highlighted section below yet. That will be coming up in future material. But for now, we have talked about a single mean, and that is the mean difference here. Okay, and this is for a paired experiment, and sometimes that's called correlated data. Okay, so I've talked about a few of these reasons for taking the difference. Okay, one that I haven't talked about is that the observation should be independent and identically distributed. Okay, so there is a correlation among twins. So like if I have some genetic factors that makes me a larger human, that makes my other twin also have or likely have those same genes that makes their brains larger. And by taking the difference, we've accounted for these genetic differences, these confounding factors that are hard to observe. Okay, and so the differences are independent, but the individual observations before differencing are not for that reason. Okay. The assumption of an identical distribution is false, okay? But when I take the difference, it is true, okay? So the difference allows us to have our hypotheses satisfied, okay? And the hypothesis of a t-test are that we have a large enough sample size, or the data is approximately normal, the data is independent, and the data is identically distributed. Okay, the differences allow us to have identical distribution and to have independence. So it's a very nice thing. So when I run the results, I calculate the difference as follows. This is just code. And then I perform this test in some statistical software, and I get this output. I perform a one sample t-test, and I get a p-value. That's what I talked about before, not the critical value method, but the p-value is equal to 0.006 or 0.6%. That means that we can reject this at the 1% significance all the way up to about the 0.6 level of significance, meaning that it's very unlikely to observe this data under the null hypothesis that the two have equal brain sizes. Okay. Now, one thing that we report is a 95% confidence interval. Notice 0 is not contained in there, so I can reject the null hypothesis at the 95% level. Significance, in fact, I can reject it all the way up to about the 0.6% level of significance. Okay. Now, this confidence interval, it says that the average difference in brain size could be as small as 0.066 cubic centimeters or as large as 0.33 cubic centimeters. Okay. And that the estimated average difference in brain size is 0.19. So schizophrenic individuals are about 0.2 cubic centimeters smaller in brain size. Okay, and so I've summarized this. What we just talked about here, that p-value is less than 1%, so there's pretty compelling evidence. The estimated difference is 0.19 cubic centimeters. And the 95% confidence interval tells me it could be as large as 0.33 or as small as 0.06 cubic centimeters. Now, if I'm going to do a test of hypotheses, you should know when you should apply it. And these are the assumptions. The data is obtained from a random sample of the population. The sample data is independent. The data is normally distributed, or the sample size is sufficiently large. And if the sample size is less than 30, you should inspect the data with a histogram and a box plot to determine if it's approximately normal. And keep in mind that minor violations to these assumptions are okay, because the test for population means is robust. Okay, so that's a very nice thing. Now, let's talk a little bit more about paired data. Okay. Paired data is when another observational unit assigned to a different treatment or control group affects the other one. And if there's a natural pairing. This is sometimes called dependent sampling because the assignment of one individual affects the other's assignment. Okay. So if I have two individuals that are similar, I'll send one to a treatment group and one to a placebo group to compare. Okay. And in this instance, we usually take the difference of the observations, and it reduces to a hypothesis test on the mean difference. Okay, and it's a single population. It's considered a single population. Okay, and this is what it means for a sampling method to be independent. The assignment of one individual does not affect another. Okay. So let's do a quick example of paired data. So an exercise scientist wants to measure how much an individual can improve their fitness after a strict treatment of diet and exercise over a 1-month period. A pre-measurement of the individual's weight is taken before the treatment, and a post-measurement is taken after 1 month. The exercise scientists believe that the treatment will reduce the mean weight of the individuals. So let's test this claim at the 5% level of significance. A sample of 36 individuals is taken, and it's found that the average difference is -5 pounds, or they lose 5 pounds. The standard deviation is 4 pounds. Okay. So for everyone, we have a natural comparison. That is their pre-weight to their post-weight. And so we're going to do a hypothesis test on the mean difference. Okay. So there's a natural pairing pre to post, and the treatment is exercise over time, diet and exercise over time. Okay, so let's summarize what we have. We're testing this hypothesis that the mean post-weight is equal to the mean pre-weight versus that the mean post-weight has decreased. So the status quo is that you haven't changed weight. What you want to establish is that the treatment of diet and exercise over time has an effect. It decreases your weight. Now, what we know how to test is a single population or a single data set, and that data set is the difference. So we're going to test that the mean difference is 0 versus the mean difference is less than 0. Okay? So here, n is equal to 36. And one important thing that you should notice is that the way in which you subtract, so I specified how I took the difference. I'm taking post-weight minus pre-weight. Okay, so pre-weight under the alternative hypothesis, this should be a negative number. I could do pre-weight minus post-weight. I just need to be consistent with how I take my difference. So your difference should be specified when you're doing this, or you should need to specify. Okay, so this is the information I have. I have 36 observations. I have 35 degrees of freedom, one less. My sample standard deviation is 4. I have a significance level of 5%, and my observed average is negative 5 pounds. So we're going to use the p-value to calculate this. I'm going to calculate the probability the sample average is less than 5 pounds. And I want to emphasize that less than comes from this alternative hypothesis. Okay, so I'm going to calculate the probability of observing the observed difference or less. So I'm going to go ahead, I'm going to subtract the mean, divide by the standard deviation, and divide by the square root of n. So under the null hypothesis, the mean is 0. So I subtract 0, I divide by the standard deviation of 4, divided by square root of 36. Oh wait, this gives me a nice t-distribution. And I apologize. That should be a t-distribution with 35 degrees of freedom. Okay, and this value is minus 7.5. So I need to go ahead and calculate the probability of t-distribution with 35 degrees of freedom is less than minus 7.5. I'm going to use the online calculator. So let's go to the list of calculators. I'm going to use the standard t-distribution. I'm going to do minus 7.5. There are 35 degrees of freedom, and it tells me it's basically 0 all the way with these many decimal places. I had to have a more powerful calculator. It can tell me with a little bit more accuracy how many zeros there are. So this is basically 0. 4 times 10 to the minus 9th has a lot of zeros, and that's less than 5%. So in other words, it's observing the data, a difference of 5 pounds or more under the null hypothesis that there's no weight lost results in a probability of seeing that of basically 4 times 10 to the minus 9th probability, or 0%. It's impossible. So we reject the null hypothesis at the 5% level of significance. You could reject it at the 1%. You could reject it at almost any level of significance. And conclude that the treatment of diet and exercises decreases in the individual's weight in the population by 5 pounds. Okay, so I'll change it to be that. Okay, and that's all that I have for today. We'll talk more about hypothesis testing later. Thank you very much.